Okay, so today we're jumping into a deep dive on a really fascinating cyber threat group. They've kind of fused old school web attacks with, well, crypto tech.
Yeah, it's quite the combination. We're talking about UNC 5142. They're financially motivated, popped up around late 2023, and they've been busy.
Busy is an understatement. They're opportunistic, hitting vulnerable WordPress sites like crazy. The numbers are, what, over 14,000 pages identified?
That's the figure, yeah. And they're using these sites to spread all sorts of nasty info stealers. Vidar, Atomic, lummac.v2, the usual suspects.
But the real story here, the thing that makes them stand out, isn't just the malware itself. It's how they deliver it, how they hide. Researchers are calling it EtherHiding.
Exactly, EtherHiding. It's basically their core strategy, obscuring the malicious parts, the code, the data, by embedding it right onto a public blockchain.
A public, legitimate blockchain.
Right. In this case, the BNB Smart Chain, or BSC. Instead of a shady domain name that can get flagged, they're using smart contracts for their command and control. It's pretty clever.
So our mission today is really to unpack that. How did UNC 5142 figure this out? How are they using this, public immutable ledger as this resilient, super low-cost way to run large-scale cybercrime?
Well, moving your C2 infrastructure off typical web servers and onto something like BSC just changes the whole game for detection and, crucially, for takedown efforts. It's a really effective evasion tactic.
Okay, let's trace the attack then. It starts with something called ClearShort. How did that initial infection happen?
It starts pretty traditionally, actually. UNC 5142 finds a WordPress site with a vulnerability, maybe an old plugin, an outdated theme, you know the drill. They gain access.
Standard web compromise.
Pretty much. Then they inject a small piece of JavaScript. Stage 1 of this ClearShort downloader, it gets hidden somewhere, maybe theme files, maybe the database, just sits there waiting for someone to visit the page.
Right, but this is where it pivots, isn't it? That first script doesn't just call out to a typical malicious server.
No, exactly. This is where the Web3 part kicks in. ClearShort, which, by the way, seems to be an evolution of an older tool they use called ClearFake. It immediately uses the web3.js library.
Which is normally used for interacting with decentralized apps, right?
Correct. It uses web3.js to connect to a public node on the BNB Smart Chain. Something legitimate like bsc-dataseed.binance.org.
Okay, wait. So the victim's browser, when it loads the compromised page, isn't immediately hitting some dodgy IP or known bad domain. It's just talking to the blockchain.
Precisely. To most security tools, that initial traffic just looks like normal Web3 activity, a browser interacting with a smart contract.
Huh. Okay.
So the stage 1 script calls a specific smart contract address. That contract runs its code.
And what does the contract do?
It sends back the next stage of the attack, usually base 64 encoded, sometimes compressed too. This code then runs in the victim's browser.
And that's when it reaches out to something more conventional.
Yes, but even then they're clever. That second stage script fetches the main ClearShort landing page, but it often pulls it from an external server that's abusing legitimate services.
Ah, like the Cloudflare Pages thing, using those .pages.dev domains.
Exactly. Abusing trusted infrastructure to make the traffic look less suspicious. Blend in even more.
Okay, so the victim's browser has now run code from the blockchain, fetched a landing page from a legit-looking service.
Yeah.
What's the final step to get the actual malware?
Social engineering. That landing page uses tricks, fake Cloudflare errors, fake CAPI-TC8s, things called click fix sometimes to convince the user to manually run a command.
Like pasting something into a command prompt or a run dialog.
Exactly that. That manual execution step is key for bypassing a lot of automated endpoint security. And that command finally downloads and runs the info stealer payload, like Vidar or whatever they're pushing that day.
Wow. Okay, so that brings us to the big advantages here. Using the blockchain, this EtherHiding thing, compared to standard C2 infrastructure. I mean, we can usually get a malicious domain taken down, right? Notify the registrar, the host.
Right, it might take hours, maybe days, but there's a process. With this, storing components in a smart contract. Well, first, it's immediate obfuscation. The malicious logic isn't sitting on a web server waiting to be scanned, it's on the BSC.
Blending in with all the other blockchain traffic.
And that leads to resilience. How do you effectively block this at the network level? It's just traffic talking to the BSC via standard protocols. You can't just blacklist the entire Binance Smart Chain. It's a huge headache for defenders.
But the killer feature has to be the immutability, right? If the core C2 logic is in a smart contract, it's permanent. Traditional takedowns just don't apply.
That's the core strength for them. The contract code, once deployed, is there forever on that decentralized ledger. It's permanently accessible. You can't seize it like you can seize a server.
Making that part of their infrastructure essentially immortal.
Pretty much. And they're not sitting still either. We've seen them evolve. Like back in December 2024, they shifted from just using base64 for their lures to using AES-GCM encryption on top of base64.
Making analysis harder.
Definitely. Raising the bar for researchers, trying to figure out what they're doing, constantly iterating.
Which brings us to probably their most significant tactical shift. Around late 2024, they moved from just using one smart contract to this really complex three-level system.
Yes, the three-level architecture. They basically adapted a legitimate software design concept, the proxy pattern, and weaponized it for incredible agility.
Right, separating things out. So you have the entry point, the logic, and the actual configuration data all in different contracts.
Exactly. It's all about making updates fast and seamless without having to touch the thousands of already compromised websites.
Okay, let's break down those levels. Level 1, the router contract.
Yes, the first level contract. Think of it as the permanent front door. The only address that the little JavaScript snippet injected into those 14,000 WordPress sites needs to know.
And its only job is?
To return the address and the ABI, the application binary interface, basically the instruction manual for the next contract. It just points the way. It's stable, never needs to change.
Okay, so the victim's browser gets pointed to the second level contract, the logic layer. This is where the smarts are.
This is where they start doing reconnaissance. It checks things about the victim's system. You mentioned those weird function names researchers found.
Yeah, like Shibuya Crossing, maybe checking the OS, or Asakusa Temple tracking where the user clicks. Kind of odd.
Yeah, maybe leaving little calling cards, who knows. But functionally, this logic contract performs checks and then decides, based on those checks, how to proceed and which configuration to grab from the next level.
Which is the third level contract, the storage layer.
Yeah.
This holds the stuff that actually changes.
Precisely. This is the dynamic part. It holds the current URL for the final payload, the current AES decryption key needed for the lure, any other settings they need to rotate frequently.
And the agility comes from the separation.
Absolutely. Think about it. One of their .pages .dev domains gets flagged and taken down. In a normal setup, panic. You'd need to update the script on all 14,000 sites. Huge effort. Lots of risk of detection.
With this proxy pattern.
They just update the storage contract. They send one transaction to change the payload URL stored in that level 3 contract. The level 1 router address never changes. The script on the compromised sites never changes. They can swap out their entire back-end infrastructure in minutes.
Okay, that's incredibly efficient.
Yeah.
But hang on. The blockchain is immutable. How are they updating that storage contract if the code can't change? That feels like a contradiction.
It's a great question, and it gets to the heart of how smart contracts work. They're exploiting a key distinction. The contract's code is immutable. Yes, once deployed, it's set in stone.
Right.
But the contract's data, its state, the variables it stores, is mutable. The immutable code includes functions specifically designed to allow certain changes to that data.
So the permanent code has built-in admin functions.
Exactly. Functions that only the contract owner, controlled by UNC 5142's crypto wallet, their externally owned account or EOA, can call.
So they just send a transaction from their wallet, calling one of these admin functions, feeding it the new URL or the new decryption key.
Precisely. The transaction gets validated on the blockchain, the function in the immutable code runs, and it simply overwrites the old data stored in the contract state with the new data. The code didn't change, but the configuration it uses did.
Okay, that makes sense. And the cost of doing this? This is where it gets really wild, isn't it?
Yeah.
Updating that critical configuration data.
It's incredibly cheap. Because it's just a simple state change transaction on the BNB Smart Chain, the network fees, the gas costs are minimal. Analysis showed a typical update costs them somewhere between like 25 cents and maybe $1.50 US dollars.
25 cents to update the C2 for potentially 14,000 infected sites.
Yep. Compare that to buying new domains, setting up new hosting constantly. The economics are just massively in their favor. After the one-time cost to deploy the contracts initially, maintenance is dirt cheap.
Which lets them stay ahead, constantly rotating infrastructure without breaking the bank. It enables this whole high-volume operation.
It's the engine behind their scale and resilience. And we saw proof they could scale this method. Remember the main and secondary infrastructure?
Right. They were running two identical parallel setups, funded and updated together.
Yeah, observed back in February and March 2025. They literally cloned their entire EtherHiding setup. It showed this wasn't just a proof of concept, it's a viable, scalable model for large-scale operations. Built-in redundancy on the blockchain.
So wrapping this up, UNC 4142 basically built themselves a malware distribution network that's, well, cheap, super agile because of that 3-level contract system, and fundamentally resilient because it's anchored to a public, decentralized ledger.
It's a significant step in cybercrime infrastructure, and while activity seemed to dip around late July 2025, well, knowing this group's track record of adopting new tech.
You think it's more likely a pause for retooling than them actually stopping?
I'd bet on it. They're probably looking at what's next, how to adapt this core idea, maybe layering it with something else, making it even harder to detect. They learn fast.
Which leaves us, and you listening, with a pretty unsettling thought. If these financially driven criminals found so much success using a public blockchain for C2, what other legitimate, maybe even mundane technologies are threat actors experimenting with right now? Are they looking at layer 2 solutions, IoT protocols, maybe even AI for orchestration, trying to build the next generation of low-cost, super resilient, hidden infrastructure?
The search for that next truly evasive C2 channel, it never really stops. They're always looking.